Today we are going to demonstrate characteristic response of a photomultiplier tube, which is commonly known as PMT. As you know, a PMT is a highly sensitive light detector, capable of detecting extremely low levels of light. Because of this property, PMT are widely used in nuclear physics, spectroscopy and medical imaging and low light experiments. In this experiment, we will study three important characteristics of a photomultiplier tube, which together determine its sensitivity and performance. The three important characteristics are: first one is the spectral response, that is the relationship between photocathode sensitivity and wavelength of incident light. Then we will study current gain, means the ratio of anode output current to the photoelectric current produced at the photocathode. And last one is the dark current. That means when no light is incident on the photocathode, a small current observed at the anode, and that is the dark current, which we are going to measure. So let us now look at the experimental setup. This is the experimental setup used to study these three characteristics. To perform this experiment, we use a PMT module, which is manufactured by Hamamatsu. This is the PMT module. This module contains a built-in high voltage power supply circuit, a 13 mm diameter side-on photomultiplier tube, which are in a aluminum housing, in a compact aluminum housing. The PMT uses a reflection mode multi-alkali photocathode, provides a gain of the order of 10 to the power 6 and has a UV glass window. So you can see this is this one actually the window. This is the UV glass window. Therefore, it shows a highly sensitive spectral response from the ultraviolet to the near infrared region. And also the PMT is connected to a control voltage unit. So this one is the control voltage unit, which allows us to set the operating voltage using a potentiometer. This is a potentiometer knob. When this unit is switched on, when you switch on this one, the desired control voltage is applied to this PMT. The output terminal of the PMT, this is the output terminal, is connected to the digital oscilloscope. The PMT output signal can be directly observed on the oscilloscope display. The DSO has an internal input resistance of 1 mega ohm, which allows us to calculate the output current from the measured output voltage. So here, the second is we have a tungsten filament bulb. This one used as the light source. The bulb is powered using a DC power supply, and a simple circuit is assembled based upon this circuit diagram. A simple circuit is assembled on a breadboard, and multimeters are used to measure the supply voltage and current flowing through the bulb. The supply voltage is maintained between 1 to 2 volts, which is sufficient for this experiment. The breadboard is placed on a laboratory jack. This is the jack, so that its height can be adjusted with respect to the detector. On a second lab jack, we mount a photodiode. This is the photodiode, circuiting along with a multimeter. This is the output is connected to a multimeter. The photodiode is placed at a fixed distance of 10 centimeters from the bulb. The position of the bulb and photodiode are carefully marked and should not be disturbed during the experiment. So at this stage we have to mount a optical filters, the filter holder, and place close to the photodiode. So now we are mounting the optical filter which is placed close to the photodiode. So the DC power supply now is adjusted to in between 1 and 2 volt, so that the photodiode output voltage lies in the range of 0.1 to 0.02 volts, and you can see the output it volts. And then we have to measure the corresponding photocurrent in microampere range when we are turning this one. Yeah, we are connecting it. So now it is showing higher value. Now if we switch off, because due to the external light source the current is relatively high, so now switching off. Now once we measure it, we are adjusting the DC power supply. And you see the current now showing. Current will be adjusted. It is showing 0.1 microampere. This measured photovoltage represents the input signal for the PMT. After fixing the input light level, the photodiode is carefully replaced by the PMT and ensuring that the PMT is placed exactly at the same position where the photodiode was there by adjusting the jack height. So we have to place same position. To study the gain of the PMT, the control voltage varies from 0.3 volts onwards in step. Now we are varying the control voltage 0.3, from starting from 0.3 volt. In between we have to keep 0.3 to 0.5 volt to fix the control voltage. For each control voltage, the corresponding PMT output voltage is recorded from the digital oscilloscope. From this data, a graph of control voltage versus gain is plotted. It is like this. To study the spectral response measurements are repeated using all available optical filters. We have different optical filters. The optical filters varies from actually 460 nanometer to 635 nanometer. Please note that the optical power incident on PMT is kept nearly constant, around 0.01 to 0.02 microwatt for all the wavelength. The control voltage of the PMT is fixed between 0.3 and 0.5 volts. Here we keep the control voltage constant by adjusting the potentiometer knob, and then the PMT output current is calculated using the known impedance of the DSO. The sensitivity of the PMT is then calculated. This is the table for spectral response. So already we have calculated the output power, that means the input power of the PMT, which is output power of the photodetector. This is the output power of the photodetector, that is the input power for the PMT. Then we have to measure the voltage using digital oscilloscope. Then you calculate the current. Then actually we have to measure the sensitivity. Sensitivity is nothing but the ratio of the output current by the input power. From this data, a graph of control voltage means the ratio output current, the process is repeated for each filter, and a graph of wavelength versus sensitivity is plotted to obtain the spectral response curve. So we are using a different wavelengths and we calculate the sensitivity, and a graph is plotted like this. To study the dark current, the tungsten bulb circuit is removed completely. The PMT module is fully covered to ensure that no external light enters to the tube. So we are covering it completely. The PMT output is connected to a multimeter. Now the output is connected to a multimeter to measure the voltage or current. We disconnected from the DSO and connect to the multimeter. Here the control voltage is varied from 0.3 to 1 volt, can vary it, and the dark current is measured after allowing about 10 minutes for stabilization. The dark current is measured in the multimeter and we have to wait for 10 minutes for stabilization. Then a graph of applied voltage versus dark current plotted. So in conclusion, in this assessment we studied the gain characteristics of a photomultiplier tube, its spectral response and the dark current behavior. These characteristics together define the sensitivity, stability and overall performance of a PMT. Thank you.